So today I want to discuss conditional probability. If you all cannot hear me, just send on the chat that you cannot hear me, and I can immediately check. Thank you. Okay, I will start now. So the first thing I want to start is today is I want to discuss what's a basic idea in probability. It's called conditional probability and base. It's a very powerful, based on a very powerful theorem in probability. And it's very widely applied in statistics and other areas. So the key notion or the key sort of fundamentals is the following. So one event has occurred. And this information may be used to either inform or alter, the the probability of another event. That's the premise of conditional probability. So let me just try and see if I can get you an idea. So let's do an example. So example 1.3.1. So let's say we toss a coin. We toss a coin, a fair coin, 3 times. So once we do that, then we immediately know that the sample space S will be these 8 people, right? So you'll have head in the 3 tosses, you'll have head, and tail, or you'll have head, tail, and head, or you'll have head, tail, tail, or start with the tail, you have tail, head, tail, head, T, tail, T, head, and tail, tail. So I have 8 possibilities: 3, 4, 5, 6, 7, 8. 8 possibilities. Then let's say I'm interested in the event that, let's say A is the event that there are 2 or more heads. This we know exactly, we know how to calculate. Now we are in this, so the observation we make immediately is that since we are in the fair coin, so we are in this equally likely outcome setting, right? That we discussed last time. So we know the probability of A is just going to be given by the size of A divided by the size of S. And that's going to be what? That's going to be size of A is size of the set what? There are 2 or more heads. So you go and pick the 2 or more heads possibility. 3 heads can happen, 2 heads can happen in these fashion, right? Then THH. And then the size of S is 8, like we discussed. So now this gives you that the chance is just 4 divided by 8, and that's the half. So chance of 2 or more heads happening is just a half. Now let's look at B. Is the chance that there is a head, in the first toss. That's the event B. Now what's this going to be again? Now the chance of B, we already know, is again the size of B divided by the size of S. And the size of B is just head in the first toss. So the first one is fixed, the second one won't be anything. So we go and write out all the possibilities. Head, tail, and head, tail, tail. Divided by size of S. And that again, you do the whole thing, it's just going to be again 4 by 8, again a half. That's clear to you, right? Now, so A and B are two different events that we understand clearly. So now this idea of information I want to use the following. So while calculating probability of A, the occurrence, let's say the chance of or probability of occurrence of A, suppose we are told that B has occurred. Okay. That, so I'll write it this way: there is a toss in the first head. There's a head in the first toss. Top in the first. There's a head in the first toss. And now, how does one? So the question then becomes, how does one compute this probability? So does this alter? So the question is, does this alter P of A? The probability. This additional information. So now this is where conditional probability comes in. So how does one do this now? So what you do is, what we again go back to the question again. So I have this event A that I'm interested in. There are 2 or more heads. B is an event that there is a head in the first toss. While doing this question, I'm told that that B has occurred. That is, there is a head in the first toss. Will this alter the probability of A? So what we do is, so the key notion is you restrict your sample space to B. So now, while understanding A, so what we do is we just say B is now a list of all possible outcomes. And so your entire sample space is now B. Okay. So this sort of intuitive idea. Intuitive. I mean, it's not quite mathematics yet, but intuitive is to think of B as the sample space now. And what is our preferred event? Our preferred event is A inside B. That is, A has occurred and B has occurred. So that means our preferred event is A on the sample space B, which is going to be equal to. So B is what? The B is just going to be the same as before, right? This head in the first toss. H, 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 T, H T H and H T T. That's the T, right? So A and B, and what is A? A was just a head in three tosses. This is going to be head, 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 two or more heads. Sorry, head H T H and H H. That's A and B. So once you do this, you're restricted sample space B. Your preferred event is this event. And again, we have to just go back to our idea that we are still in this equally likely setup. Outcome setting. So our probability should be equal to, so the probability of A given that B has happened, B has occurred, should be the size of A and B divided by the size of B. And that turns out to be what? Size of A and B is 3, size of B is 4. This is one way of understanding this probability. So suppose you want to know, like I said, you have this simple experiment of tossing a coin 3 times. And then you sort of, you know that there's a head in the first toss, and you're interested in the chance of occurrence of A, which is 2 or more heads. What you do is, you restrict sample space to B. That's B is already occurred, so you're inside B now. Then what you're interested in is A and B. You're the equal likely outcome setting, so the probability of A given B is just A and B divided by 3 by 4. That's one way of solving this problem. So what are the pitfalls of this idea? So one is that it's a bit inconvenient. So it's a bit inconvenient because to solve a problem this way, every time uh, we would have to change sample space. So moment and event is given. Okay, you say fine, rework the sample space, rework all your events, change your probabilities and some stuff. But the idea is that the key idea is it does provide a method to calculate the conditional probability of A given that B is occurred. So how does one generalize this? Let's just see how to sort of make this idea a little bit more. It provides a framework. Let's try and see if we can grab the framework properly. So the idea is that this is denoted by sorry denoted by probability of A given B. So now, how does it provide the framework? So the framework is the following. So the framework is, suppose mod S is finite. That is, then so I want to understand. I have two events A and B, and let's say chance of B is positive. That is, B has occurred, and probability of A given B, the above says, is going to be A and B divided by A. Okay, this is what the above says. This is from above. But what we do is we sort of think about it a little bit more carefully. You divide top and bottom by S, so you get A and B, divide by S, the size of S. The whole thing divided by B and the size of S. Now you know, if you're on the equal likely outcome setting, suppose you're on the equal likely outcome setting, outcome setting. This is going to be the probability of A and B at the top, and the bottom is going to be probability of B. So this leads to this idea. So you can look at the the left hand side. That's what we're interested in understanding. Start from here and look at the right hand side that we end up with. This provides a certain framework of understanding conditional probability. So this leads to a definition of conditional probability for general sample space. So let me define it now. Okay. So here's the idea. So here's the key definition. The definition is 1.3.2. This is called conditional probability. So here I go and say that let S be a sample space. So any countable set with probability P. So I'm sorry, I just said countable set, but a priori we don't have to assume that for this definition. S can be any sample space with probability P. A and B be two events. With probability of P is positive. Then the conditional probability of A given B, which is written as the probability of A given B, so it's defined to be, so defined to be probability of A given B is given as probability of A and B divided by probability. That's the definition of conditional probability we'll use. So the key idea is that this definition allows us to sort of definition makes it possible to compute conditional probability the key is that you don't have to keep on changing sample spaces in terms of the original probability function, original sample space and probability. That's the advantage of it. let's do a quick example and then let's come back to this in a second. Okay, thank you. So now let me try the following. So let me go to example 1.1. So here the example is the following. A pair of dice are thrown, or rolled, let's say. And then let's say we have the event we know as it is known that one of the dice shows up